Hello, everyone, and welcome to the COP27 Cryosphere Pavilion. We have our final ECS presentation today, Early Career Scientist Program, for week one. I am happy to introduce Dr. Ella Gilbert, who works as a regional climate modeler with the British Antarctic Survey. Ella, the floor is yours.
Thanks. Thank you, Amy. So yeah, really excited to be able to talk a little bit about some of my research today. So as Amy said, I'm a climate scientist at the British Antarctic Survey. I'm also a climate modeler. So I mostly use computer modeling to understand the past, the present, and increasingly the future of polar climate. I've also ended up working quite a lot on ice shelves, so these floating platforms of ice around Antarctica, and how the atmosphere and the climate actually interacts with those in the context of climate change. So this talk is a little bit about some things that I'm currently working on, a little bit of kind of background, and mostly focusing on Antarctic ice shelves. Also, a big shout out to ICCI for bringing us all here and allowing us the lovely opportunity to speak at COP27. So I thought I would start with a story, which is a bit more of the kind of why. So this picture was taken on the Larsen C ice shelf when I first went to Antarctica in 2017. And it was such an incredibly life-changing experience. Actually going, as a climate modeler, we spend a lot of time sitting behind a desk. We don't often get to experience the environment that we're working on the whole time. So it was really incredible for me to get to go put my actual feet on the ice shelf that I spend my entire working life thinking about. It really struck me as we kind of touched down, and you can see in this picture, there's nothing beyond the immediate place that we landed that you can see any kind of human influence. There's nothing as far as the eye can see. And it really impressed upon me the significance and the importance of the polar regions, which is part of why I'm working on this project, which is basically looking at how the polar regions are currently, how all the different elements of the polar regions interact, and how they're likely to change in the future. So this project is called PolarRes. It's an EU-funded project. It brings together huge numbers of researchers from all over Europe and beyond, actually, in an interdisciplinary project. And it's one of the first projects that's exclusively modeling based in this kind of framework. And the idea is that it helps us to understand how processes are going on in the polar regions as they are. And that's some of the things that you can see in this kind of schematic over here. And it's also trying to project the future of the polar climate. And then finally, it's the main real tangible outcome is going to be using those physical climate changes to predict and project future climate impacts on things like wildfire risk, on permafrost thaw, on transarctic shipping, on people's lives and actually their livelihoods every day. And one of the primary methods that are going to be used in this project is this idea of storylines. So typically when we think about climate change, we think about average global temperature rise. And whilst average global temperature rise is very important, increasingly we want to know more about how climate change is likely to impact specific regions. How is climate change going to affect coral reefs in Sharm el-Sheikh, or water resources, or sea level? All of those things are really important when we're thinking about impacts, because that's what actually people care about for their lives, for their livelihoods. So this is a slightly different approach to thinking about future climate. It takes these sort of narratives of how greenhouse gas emissions and human activity shape things like atmospheric circulation, so wind patterns or sea ice. And it takes these sort of narratives or stories of what might happen in the future, and we're using those to explore how climate change is going to impact the polar regions. So for the Arctic, for example, how sea ice extent, which Bima has already given us a great introduction to, is likely to impact things like transarctic shipping. Or, for example, in the Antarctic, we're focusing on how the strength of the winds that circle Antarctica are going to impact the local temperature, local ice loss, these sorts of things. And just a brief justification is that, we can trust global models which cover the entire planet very well for that big picture, that global temperature rise. And that's something that we can see in this animation, which is showing the successive different predictions of climate throughout time from the 1970s. And it's actually been really successful climate modeling, global climate modeling, at tracking those predicted temperatures. So the black line is what's actually happened, and then successive forecasts are shown in the animation. But whilst we have good confidence in these global models at getting things like temperature, things that are a little bit more tricky to represent in climate models, things like precipitation, for example, things that really matter for the polar regions, things like ice sheet changes, those are much more difficult to capture at that sort of scale. And this is where regional climate modeling comes in. And I like to think of regional climate modeling as kind of like taking a magnifying glass to zoom in on a very particular area of interest. So in this instance, it's something like the Arctic or the Antarctic, but it basically allows us to focus in on a specific area of interest and get a much more detailed picture of what's going on. And that increased resolution, that increased kind of complexity allows us to get a much better picture and allows us to predict the future much more accurately. It's also really, really helpful in regions where we have limited observations. So where it's very difficult, for example, to go and collect data in remote parts of the Antarctic or the Arctic, or in winter, for instance, it can be really important and really helpful to sort of get a consistent record of what might be happening. One of my favorite quotes of all time as well is that models are all wrong, but some are useful. And I think this is very important to keep in mind, but I think they're also even more useful when we have a lot together. So when we have what we call an ensemble. So an ensemble is basically a whole bunch of different models simulating the same thing, and eventually you get a consistent picture, you hope. So in this diagram, the individual blue lines are kind of specific model, what specific models think will happen with temperature over time. You can see that they're all subtly different. And then there's this black line, the ensemble average, which goes through the middle. So we're not necessarily that fussed about what happens with the individual blue lines. What we care about and what matters is the general trend, the general picture that we can get from all of them together, because we don't know what the specific strengths and weaknesses of each of those individual models with those blue lines are. But if they're all pointing roughly in the same direction, that gives us a consistent message that what they're saying is more likely to be correct. And also, if we have that range of different models, we can get an estimate of the range of plausible future outcomes. So what we would call uncertainty as a kind of spread of possible outcomes. What that looks like in real life is a lot more messy. So this is a similar sort of plot. This is a time series of precipitation. So one of the more difficult things to simulate with models over the entire Antarctic ice sheet for the satellite period from 1979 all the way to 20